Welcome to Bedtime Astronomy. Explore the wonders of the cosmos with our soothing bedtime astronomy podcast. Each episode offers a gentle journey through the stars, planets, and beyond, perfect for unwinding after a long day. Let's travel through the mysteries of the universe as you drift off into a peaceful slumber under the night sky. Dancing through the cosmos. A journey into the mechanics of space orbits. In the vast expanse of space, celestial bodies move in defined paths known as orbits. These orbits are the gravitationally curved trajectories of objects around a point in space, such as planets orbiting a star or moons orbiting a planet. Understanding these orbits is fundamental to astronomy, space exploration, and comprehending the dynamics of our universe. The concept of orbits dates back to ancient civilizations, but it wasn't until the 17th century that Johannes Kepler and Isaac Newton formulated the laws that describe these motions. Kepler, a German astronomer, introduced three fundamental laws of planetary motion. His first law stated that planets move in elliptical orbits with the Sun at one focus, challenging the then prevailing belief in perfectly circular orbits. His second law, known as the law of equal areas, described how a line segment joining a planet and the Sun sweeps out equal areas during equal intervals of time. This means that planets move faster when they are closer to the Sun and slower when they are farther away. Kepler's third law provided a relationship between the time a planet takes to orbit the Sun and its average distance from the Sun, stating that the square of the orbital period is proportional to the cube of the semi-major axis of its orbit. Building on Kepler's work, Isaac Newton formulated his law of universal gravitation. Newton's law states that every mass attracts every other mass in the universe with a force that is proportional to the product of their masses and inversely proportional to the square of the distance between their centers. This law explained why planets follow elliptical paths around the Sun and how objects influence each other through gravitational forces. Orbits can take various forms based on their shapes and the objects they involve. The simplest form is the circular orbit, where an object moves around a central body in a perfect circle at a constant speed and distance. Many artificial satellites around Earth follow circular orbits. Most celestial bodies, however, follow elliptical orbits, where the distance between the orbiting object and the central body varies, leading to changes in speed as the object moves along its path. Comets and planets are examples of objects in elliptical orbits. There are also parabolic and hyperbolic orbits, which are followed by objects not bound to the central body and will eventually escape its gravitational influence. Parabolic orbits occur at the exact escape velocity, while hyperbolic orbits occur at speeds greater than the escape velocity. Orbital mechanics is the study of the motions of artificial and natural celestial bodies under the influence of gravitational forces. It encompasses the principles and equations that govern the behavior of objects in space. One of the fundamental concepts in orbital mechanics is the velocity required for different orbits. Orbital velocity is the speed an object needs to stay in orbit around a planet or other body. For example, the orbital velocity for an object around Earth is approximately 7.8 kilometers per second. Escape velocity is the minimum speed an object must have to break free from the gravitational pull of a planet or other body, which for Earth is about 11.2 kilometers per second. Placing a satellite or spacecraft into orbit involves precise calculations and powerful rockets. The launch process can be broken down into several key phases: liftoff, ascent, and orbital insertion. The rocket launches from the ground, overcoming Earth's gravity, travels upward through the atmosphere, and finally achieves the correct speed and trajectory to enter the desired orbit. If the speed is too low, the object will fall back to Earth. If it's too high, it will escape Earth's gravity altogether. Once in orbit, spacecraft often need to perform maneuvers to adjust their paths. These maneuvers include the Hohmann transfer, a fuel-efficient way to transfer between two orbits by performing two engine burns; the bi-elliptic transfer, a more complex maneuver involving three burns used when the change in altitude is significant; and plane changes, which adjust the inclination of the orbit to align with a desired path, usually more fuel-intensive than other maneuvers. Different types of orbits serve different purposes. Two of the most important for satellites are geostationary orbits and low Earth orbits. Geostationary orbits are positioned about 35,786 kilometers above the equator and allow satellites to match Earth's rotation. As a result, a satellite in this orbit appears stationary relative to a fixed point on the ground, making it ideal for communication and weather satellites. Low Earth orbits range from about 160 to 2,000 kilometers above Earth, where satellites travel much faster and complete an orbit in roughly 90 minutes. This orbit is commonly used for Earth observation, reconnaissance, and the International Space Station. Tidal forces, caused by the gravitational interaction between a planet and its moon or other satellites, can have significant effects on orbits. These forces can lead to tidal locking, where one side of the orbiting body always faces the planet, as seen with the Moon and Earth. Orbital stability is crucial for long-term missions, with factors affecting stability including gravitational perturbations from other celestial bodies, atmospheric drag for low-altitude orbits, and the Yarkovsky effect, where an asteroid's orbit changes due to the way it absorbs and re-emits solar energy. The history of orbital mechanics is rich with milestones. The launch of Sputnik 1 by the Soviet Union in 1957 marked the beginning of the space age, as it was the first artificial satellite to orbit Earth. The Apollo missions demonstrated complex orbital maneuvers, including lunar orbit insertion and docking in space. The Hubble Space Telescope, launched in 1990, has provided unprecedented views of the universe from its orbit around Earth. Now, imagine standing on a high mountain and throwing a ball. If you throw it gently, the ball will fall to the ground nearby due to gravity. Now, imagine throwing it harder. The ball will travel farther before hitting the ground. If you throw it with enough speed, something interesting happens. The ball will keep falling toward the ground, but because the Earth is curved, the ground keeps falling away from the ball. If you could throw the ball at an incredibly high speed, it would keep falling towards Earth but never actually hit the ground because the ground curves away at the same rate. Essentially, the ball would keep falling around the Earth in a circular path. This is what we call an orbit. In space, satellites are launched at such speeds so they continuously fall around the Earth without ever hitting it. The Moon also provides a perfect natural example of an orbit. The Moon orbits Earth due to the gravitational pull exerted by our planet. At the same time, the Moon has a forward velocity that prevents it from simply falling into Earth. This combination of forward motion and the pull of gravity creates a stable orbit. Imagine the Moon as that fast-moving ball we discussed earlier, but instead of being thrown, it naturally acquired its speed during the formation of the solar system. The balance between the Moon's inertia, its tendency to move in a straight line, and the gravitational pull of Earth keeps it in a continuous orbit around our planet. Orbits are all about balance. Gravity pulls the object inward, while the object's inertia, or forward motion, tries to move it in a straight line. When these forces balance perfectly, the object follows a curved path around the central body. If inertia is stronger, the object will spiral outward. If gravity is stronger, it will spiral inward. Artificial satellites mimic this natural balance. For example, the International Space Station, ISS, orbits Earth at about 28,000 kilometers per hour, 17,500 miles per hour. At this speed, the ISS falls towards Earth but moves forward fast enough that the curve of Earth falls away beneath it. This keeps the ISS in a stable low Earth orbit, allowing it to circle the planet approximately every 90 minutes. Understanding these basic principles of orbits, illustrated by throwing a fast-moving ball or observing the Moon's motion, provides a foundation for grasping how objects move in space, whether they are natural celestial bodies or human-made satellites. The future of space exploration is promising, with advancements in technology enabling new missions and capabilities. Companies like SpaceX are developing reusable rockets to reduce the cost of reaching orbit. Future missions aim to explore beyond Earth's orbit, including missions to Mars, asteroids, and beyond. As more objects are launched into orbit, managing space debris becomes critical to ensure the safety and sustainability of space operations. Understanding orbits is fundamental to our exploration and utilization of space. As technology advances, our ability to navigate and utilize these celestial paths will continue to expand, opening up new possibilities for discovery and exploration.